So let's finish up section 3 by doing some more examples. We looked at 2 examples, both which were examples of permutations, and that was because the order was important, meaning that whether you're president, secretary, or treasurer, that's important. Whether you win the race, second place, third place is important. So those meant that we used the permutation formula, and the big number is always the number that the number of people or choices that you have, and the smaller number is the subset that you're creating. So if you have 30 people and 3 officers, 30 is N and 3 is R. And we have our factorial formula, which then we simplified by rewriting the larger factorials in terms of the smaller factorials. So the next one, problem number 24, says how many ways can a sample of 5 cell phones be selected from a shipment of 24 cell phones? So the question is, does it matter what order I pick the 5 phones? If I pick the same 5 phones, but I picked, let's say for example that I've numbered the cell phones, and if I choose 5 cell phones, say cell phones 2, 7, 11, 16, 21, and I choose them in that order, does it matter if I pick them in the order shown here? And the answer is no, because it's still the same 5 cell phones. They are still part of the sample. There's no, the first cell phone that I picked doesn't have any priority over the second phone that I select. So in that case, order is not important, and therefore I used combinations instead of permutations. So we're going to kind of answer the question here. The questions that you want to ask yourself when solving these problems is number one, is order important? In this case, no. So if the answer is no, then you use combinations. And then you look on your sheet of paper that tells you what the formula is. And so for combinations, we use the letter C. The larger number is the first subscript, and the second number is the smaller number is the second subscript. And then we have the formula, which says if you take 24, you have 24 items, you select 5, where order is not important. The result is n factorial divided by r factorial times n minus r quantity factorial. And n is 24, r is equal to 5. So we plug those in, so you get 24 factorial divided by 5 factorial times 24 minus 5 quantity factorial. So that's just a matter of plugging the numbers into the formula. And then we just have to evaluate that. So what I want you guys to be able to do is not have to use a special calculator. So we rewrite, well actually the first thing we do is we do the math inside the parentheses. So 24 minus 5, which you can do in your calculator. Hopefully you can do that in your head. And then we rewrite the numerator as slightly differently. So we start multiplying by subsequently lower numbers until we get the larger of the 2 factorials that are in the denominator, which in this case is 19. And then we can cancel out the 19 factorials. So then we have something more manageable to do as far as calculating the answer. And so we'll have 24 times 23 times 22 times 21 times 20 divided by 5 factorial, not just 5, but 5 factorial. Now, at that point, you probably could do it in your calculator without any sweat. You could actually even simplify this further by looking at the terms in the numerator and seeing if any of the product of the two terms of the denominator equal the term in the numerator. So does anybody see a number that, two numbers in the denominator which multiplied together equal one of the numbers in the numerator? There's actually one where there's three of them if you wanted to do it. So you could simplify it. Yeah, Eli. Which one? Yeah, 5 and 4 gives you 20. The other option you could do 4 times 3 times 2, which is 24. You cancel out with that 24. You don't need to do this. If you just like to do mental math, then you can simplify it even further. So the 20s cancel out, and then 3 times 2 is 6. 24 divided by 6 is 4. So if you do those additional simplifications, you only have to multiply 4 numbers together. But I'll leave it up to you. So I get 42,504. So what that's saying is that I can pick 5 cell phones out of 24, and there are 42,504 different samples that I could collect, which is a pretty big amount. But where would this have applicability? Say you're using a new shipping supplier for your cell phones. You're manufacturing cell phones, and you say, okay, I want to know how well they do, and you don't want to check every cell phone. So you ship 24, and you say, oh, I'm going to randomly select 5 because I think that's enough to give me an idea. So then you open them up, and you look at them, and you see whether they're damaged or not. The other 19 you can sell, or you can reuse because you haven't done anything with the packaging. So this does have, it's a real life kind of situation. Okay, so this is a lottery game. It says in the 739 lottery, you select 7 distinct numbers from the set 1 through 39, where order makes no difference. How many different ways can you make your selection? So the purpose here is that, what are the odds of winning the lottery? Because there are going to be so many different combinations. And again, normally you pick your lottery numbers from the lowest number to the biggest number, but there's no reason that you can't pick it any other direction because it's still the same 5 numbers. It's like being dealt cards. You may organize them yourself, but they're still the same cards, whether you have the 3 of a kind and then the 2 of a kind, or the 2 of a kind and 3 of a kind, same stuff. And they just very explicitly say that order makes no difference. So they're saying order makes no difference. So is it a combination or is it a permutation? Combination. Okay. So we say, okay, good. We answer the question, is order important? In this case, they tell us directly, so we don't have to think very hard. So, but we'll still write it down, just so we always ask this question: is order important? Question mark. The answer is no. Okay. Since no, use combinations. So we're going to use combinations. The larger number is the number we're choosing from. We're choosing 39. We have 39 numbers to choose from. We're choosing 7 numbers. The formula for combinations is n factorial over r factorial times n minus r factorial. And we know that n equals 39 and r equals 7. So we get 39 factorial divided by 5 factorial times 39. What did I do? 5. 7. 7 numbers, not 5 numbers. So if you can get your calculators out, see if you can come up with the, I'll let you do the rest of it. And for you folks online, if you can come up with an answer, and then when you get an answer, raise your hand so I can hear. Actually, I need to take off the mute, I think, or I can't hear you. So it'll be a pretty big number, probably on the order of millions. millions of different combinations. And what I'll do is I'll put the previous slide up just in case you didn't write it down, so you can see what I did. Let you do the rest. Now, do you have it on your calculator, or did you do it the long way? Okay, good. Okay. Yeah, looks like it's in the realm of possibilities in terms of, looks like your math's correct. So now that I've given you a minute head start, I'm going to write this stuff down. Actually, I left off a step. This is probably the point that you wish you had a calculator that did this without having to do factorials, but most of the time you don't have to worry about it. So I got that number. See if anybody put anything in here yet. So to show me that you are paying attention, write that number in your chat window and enter it in. Okay, so it's 15,308,937, which is a lot of choices. We said it was about going to be so many million. The California Mega Lottery, what I'm going to ask you to do is to, well, we'll talk about it. Well, we can still do the calculation, it's not that bad. But it's basically the same concept, except, and it's like Powerball, I guess, right? Powerball's similar to that. I'm not sure how many numbers you choose from, but so we have two parts. We have the 5 numbers, and then we have the mega number. So these are like 2 steps. Step 1 is to choose your 5 numbers, and step 2 is to choose the second number. And therefore, it's a 2-step process. So you find out how many combinations or subsets you can get from the first part. And the second part's easy. It's 27. Right? There's 27 possibilities, and then you multiply them together. So you get the number for the first part, and you multiply it by 27, and that'll give you the total number of possibilities. Now it's because, again, the order is not important. You could create a lottery game where order is important. The problem there is that what is the problem? I mean, there's no problem. It's just less. The odds are lower that you're going to win. So you might have. But we'll ask that question. What if the order was important? How many choices would there be? But in this case, we're saying order is not important. So what you would do to get the answer here is you would take 47 things, taken 5 at a time. That would give you the first part. And then you'd multiply by 27 taken 1 at a time, which is always just 27. Anything you take so many 1 at a time, it's just the number itself, the first number. And then the second one is going to be 47 factorial divided by 5 factorial times 47 minus 5 factorial. Let's see if anybody put a number in yet. Oh, good. They're paying attention. Good. So go ahead and see if you can get that one. So make sure you can get that answer. 41,416,353. You know, you're going to design a lottery based on how many people play on an average, and how many on average, how many games do you have until somebody wins? I don't know what the chances are of winning. The first time the new lottery comes out, how many people actually play? You know, 4,000 people play and you've got 41,000 choices. The chances are 1 in 10 that somebody's actually going to win the first time. And normally what happens is the larger the jackpot, the more people play. So that, but every time it's played, the odds are the same for winning. It's not like now the amount you win is higher the more times the more people who are playing, because of the way they determine the prize. It's not like it's fixed prize every time. It's based upon how many people play. I was just thinking about this. I did this without writing anything down. I guess after a while you think all you have to remember is take 47 and go 5 numbers. So on my calculator I just calculated 47, 46, 45, 44, 43. I said, oh, there's 5 numbers. That's going to be how far I have to go down to cancel this out. And then I know that then the denominator was just 5 times 4 times 3 times 2 times 1. So I guess ultimately the number of terms I have here, 1, 2, 3, 4, 5, 6, 7, has to be the same number of terms that are in the denominator when you simplify it in these combination situations. So I have 7 numbers in the numerator and I have 7 numbers in the denominator. So it would be easy. You could, if you got lazy and said, I know what's going to, you could always check yourself that you went down far enough just by doing an accounting of the number of things that I'm multiplying together. And again, this all goes back to the fundamental accounting principle, which says that, I've got a 7, in this case, the previous one, I've got a 7-part process. The first one is I'm choosing one number out of 39. Once I choose that one number, I can't use it again, so then I only have 38 numbers to choose from. And I do that for each one of the 7 steps. And that gives me the total number of arrangements of 7 numbers from 1 to 39, where order is important. And then I divide by this, because if I have 7 numbers, I can arrange those 7 factorial ways. That's what this part is. This is to remove the importance of order by dividing by 7 factorial. Okay. How many cards must be drawn without replacement from a standard deck of 52 cards to guarantee that 2 cards will be of the same suit? Okay, so you look at that and you're saying, what's that? No. So this is in here just to show you that don't always revert to using a formula. Sometimes you get to the point where you're like, there's got to be a formula I got to use, and so does the formula apply here or not? And you can see I'm not, it says guarantee 2 cards. You might say, okay, 52 things taken 2 at a time, but that's not what the question is. You have to actually you have to kind of think of it don't get seduced into, oh, it's from this part of the chapter and therefore I just have to use the formula. It's not a formula question. It's more of a kind of a logic question. So you think about, well, let me see what would happen. Let's just think about, if I pick a card. So the first step, I'm just going to say step 1 here. Choose a card, okay? And it's going to have to be of one of 4 suits. There's 4 suits when you pick a card. So let's say, for example, I get a heart. So step 2, so there's 4 possibilities in this case. There's always 4 possibilities. Choose a card. Okay, so if I chose a heart, I'd have 2 cards of the same suit and I'd be done. So I could finish in a minimum of 2 steps if I got a heart the second time. But what they're asking here is to guarantee that 2 cards will be the same suit. Well, I can't guarantee that 2 cards will be the same suit because I may choose something different than a heart. So so what I would say is there are 3 possibilities that I would have that wouldn't have 2 cards of the same suit would be spades, diamonds, and whatever the other one is, clubs. So let's say I pick clubs. So I can keep going now because I've still got cards of different suits, and I choose a card again. Choose a card. So to have it so that I don't have the same suit, but there's only 2 to choose from now. There's only 2 possibilities, which is a diamond or a spade. And step 4, again, the only suit that I can choose that will allow me to keep doing this without having what do they call, what's the word they used? 2 cards of the same suit. So now I've got 3 different suits. The only one left is spades. Then when I get to step 5, my 5th card, I've already used all the suits up. So at this point, when I pick my 5th card, it's got to be either a spades, diamonds, clubs, or hearts. And so the answer to this question is 5. I can guarantee that if I give you 5 cards, that 2 of them are going to be of the same suit. That's the whole concept. So that's just to show you don't get lulled into a false sense of security. Okay, here's another one. Number 37 in the book. Most stations that were licensed after 1927 have 4 call letters starting with a K or W, such as WXYZ in Detroit or KRLD in Dallas. Assuming no repetitions, how many 4-letter sets are possible? Count all possibilities, even though practically some may be inappropriate. I'm trying to think of 4-letter words, the bad 4-letter words that start with the W. Anyway. So again, this is a case where you might be tempted to use combinations or permutations. It says no repetitions are allowed. So that would tell you, well, if I could use either one of those, well, that's not telling you either one, because in the case that we did, repetitions were not allowed. So that doesn't, order is important. So you might be tempted to use permutations. But the problem is, it's not like you To use permutations or combinations, when you go through the various steps, you have to have the you have to start with the total number of options, like 26 letters. So if I were able to make a radio call letter that it could be any letter in the first space, and order was important, and you couldn't use repetitions, then I could use permutations. But because the first one is not all 26 letters, it's not a simple permutation problem. So if it's not a simple permutation problem or a simple combination problem, you have to go back to the fundamental accounting principle, which is what we're using in permutations and combinations. This is just a special case. So the way you would do this is you would break it up into a 4-part process and ask the question, how many choices do you have for each step, and then multiply all those numbers together. So number 1, choose first letter. So how many possibilities are there for the first letter? 2. Okay. Choose second letter. So it says no repetitions, but the second letter can be any letter in the alphabet. But I can't repeat the first one I had. So how many choices do I have for my second letter? 26 or 25? 25, yeah. So if I pick W, it can be any letter except W. If I pick K, it can be any letter except K. So then for the third letter, again, I'm not allowed repetitions, so it becomes 24. And the fourth step is choose fourth letter, which now there's only 23 letters left. So that's the 4-step process. Those are the number of choices that I had at each step. And I can use the fundamental accounting principle. The requirement is that the number of choices is independent of what I choose in the previous step. So if I choose W, it does limit me to not using W, but it doesn't reduce the number of options. Whether I choose K or I choose W, I still get 25. So that's why I can use the fundamental accounting principle. So you would call this N sub 1, this N sub 2, N sub 3. The subscripts refer to the step. So the number of arrangements equals 2 times 25 times 24 times 23. So it's 27,600 radio stations, which, is that a reasonable number of radio stations for the country? Let's try it. 27,600 divided by 50 states. That's 552 radio stations per state. Yeah, you won't need as many. Yeah. What is it called? And you don't have to worry about mountains getting in the way. Flyby, that's what they call it, right? Flyby states. Yeah, I've never actually driven through something like Nebraska or Kansas or. Okay, so license plates. You're starting a new state. You got to figure out how many things you need on the license plate. So there are all different rules probably for different states on what the combinations. But what I'm going to assume is 3 letters, 3 numbers. Of course, order is important. And I'm going to say repetitions allowed. And we're not going to worry about swear words. So how do I approach this? Again, it's not a clear, well, because repetitions are allowed, that wipes out permutations and combinations. You can never use permutations and combinations if you allow repetitions. And the fact that the number of letters to choose from is different than the number of numbers to choose from. I'm not gonna, and let's say no 0 in first digit. Okay, so I'm going to do that. So again, it comes down to a fundamental accounting principle problem. So you're going to have 6 steps. So I'm just going to write the steps down. The steps are going to be to choose letters, number of choices. So this is letter, 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 number, number, number. So I'm going to let any letter be the first one. I'm going to let any letter be the second one, any letter be the third one. So that happens. That's what happens when you have no when repetitions are allowed. Is you can use it over again. So instead of 26 times 25 times 24, you just have 26 times 26 times 26. So it doesn't involve factorials. And then letter numbers, you have. If I don't let myself use a 0 here, there are only 9 numbers to choose from instead of 10 numbers. But then if I do let zeros be used for the remaining 2, so these are each individual step in the process. And so the number of arrangements, which are the total number of license plates, is just going to be 26 times 26 times 26 times 9 times 10 times 9. And I bet it's going to be a pretty big number. So that comes out to 15,818,400. So here's a little trivia fact. In England, the license plate can tell you when you buy the car. So they changed I think it's the first letter is based on the year it was made or bought. And I figure after 26 years that the car is probably going to be antique by then. And you probably know that it's not 1 year old, it's 27 years old. And they have a special name for it. I'm trying to remember what it is. Let me see if I can let me find it on the internet here.
So your attendance question is to look up online how many different arrangements of the 3x3 Rubik's Cube are there. So let me just write that down for you. So Rubik, everybody's seen those. So as you know, there's 6 different faces and there are 6 different colors, and you're trying to get all the colors of the same type on one side. And I guess the second question for you is, have you ever solved the Rubik's Cube puzzle? And usually that involves using some kind of an algorithm, which I did learn because my wife wanted to teach it for one of her classes. But then I tried to do it a couple years later and I'd forgotten how to do it. So anyway, just search for Rubik's Cube combinations. And let me know what that is. It's a big number.
Anyway, I can't find anything. But anyway, that's different than the U.S., which I thought you might find interesting. The other interesting thing is phone numbers. I'm going to show you this. Let me just
postal people drive cars with the driver's seat on the
no, because they don't have mailboxes like we do at the road. So you have to the post box is on the house. Well, typical, and I'll show. Well, actually, they usually have a slot in the door. So that's not made up. That's true. So the phone numbers in England, they have different formats depending upon how big a place you live. So they have these special digits. 999 is like our 911, so that's emergency. And then you have, depending if you live in a big city like London, you typically have like 02 or something like that. And then all the other numbers are your individual number. But if you live in a small town, then what you typically have is 7 digits, and then your last 4 digits are your local number. So my aunt and uncle that we used to stay with when we went to visit when I was older, you used to be able to dial a local number with just 4 numbers. So we're able to dial a local number with 7 numbers. There, you would dial a local number with 4 numbers. Their local number was they would always say 2006, and they would always preface when they answered the phone. They wouldn't say hello. They'd always say, well, they might say hello, and they go, Bakewell 2006. Well, Bakewell is the town that they live in. So that was kind of the weird way of answering the phone. Instead of, it's like we would answer the phone and I'd go 968-2888 instead of hello. So if you go to the the first 5 digits of the phone number for where we usually visit, the town is called Matlock. It's 01629, and so that's 5, and then it's a 9-digit number, so you have 4 more numbers, I think. Still 2006, but it's got 01629. Whereas, so that's as many. You have five numbers that tell you where your locality is. And mobile numbers, they start with a 07, so you know it's a mobile number from that. But like London is 02. But if you go to these smaller places, it ends up having more digits. So it's a interesting arrangement.
Is that Wales and everything?
Hmm?
Is that Wales and
Yeah. Yeah. Yeah, probably Northern Ireland too. Okay. So the same thing you could do with telephone numbers. If you had certain restrictions, you would see what the rules are for each letter that's chosen, and you would make it into a fundamental accounting principle. Okay. This is an interesting one. It's one that I would never give to you, and I'm not sure if I figured it out the first time. I might have had to cheat and look at the answer book, but so I'm just going to show it to you. In how many ways could 15 people be divided into 5 groups containing respectively 1, 2, 3, 4, and 5 people? So it's kind of like a 5-step process. You choose 1 person for a group, then you choose 2. So out of the 15 people, you choose 1 to be in 1 group. Then you have a 2-person group, so then you choose 2 people out of the remaining 14. And then you've got 1 plus 2 is 3, which means there's 12 people left. So out of the remaining 12 people, you choose 3 people for the next group. So they're groups which order does not matter. So this means we are going to use combinations to answer this question. Then when you picked 1, 2, and 3, that's 6 people, so that means there's 9 people left. You have 9 people left to put in a group of 4, and then you have 5 people left, which you stick in the remaining group. So the way you would solve this problem is you would do it this way. So first thing you would do is you'd have 15 people, and you would choose 1 person. The second step, you would have 14 people left, and you would choose 2 people out of those 14. Then you would have 12 people left, and you would choose 3 people out of those 12. Then you'd have 9 people left, and you would choose 4 out of that. And finally, you would have 5 people left, and you would choose 5 people out of that. You mean that this one here? 1. Yeah, this is actually equal to 1. That is equal to 1. This is equal to 15. The ones in between are a little more complicated, but not that much complicated. I mean, we just use the formula. This number is always that number, this number minus that number. 14 minus 2 is 12. 12 minus 3 is 9. 9 minus 4 is 5. Now, you could go the other direction. So what you could do is you could pick 5 people out of the 15 instead of 1 person. That would leave 10 people left. So then you would have 10 people left, and you would choose 4 out of those 10 people for a group. That would leave 6 people left, and you could choose 3 people out of those. And 6 minus 3 is 3, so then you have 3 people left. You can choose 2 people out of those 3, and then you would have 1 person left, and you would stick them by themselves in a separate group. So, and you could pick the 3-person group first and the 4-person group second, and there's all these endless possibilities of what you would get in terms of the number of different ways. So the question is, if I go this direction where I choose the 1-person group first and then go to the 2, the 3rd, the 4, or 5-person group, or if I start with 15 people, I choose the 15-person group first, then the 4-person group, then the 3-person group, 2-person group, do you think that would make any difference? It seems like, based on the numbers, the chances of those being exactly the same is pretty small. So if you actually do that, if you go through the math, you could just plug the numbers in and you get 2 numbers. I don't know what the numbers are. I don't want to spend the time doing it. This is more just a thought problem. Or I could write out, all the factorials that are involved here, and then expand them, and see if all the terms in the numerators and all the terms in the denominators turn out to be the same, so that they are the same. Well, the answer is yes. They are the same. It doesn't matter whether you choose this direction or that direction. Even though it looks like it's not got to have much chance of actually working out, it actually does give you the same number. And you could pick your groups in any order. So it's kind of neat that it does work out. You just have to believe me, but I actually did go through the math and show that it does come out to be the same thing. So that's a okay. So I've already assigned that, right? So there you go. Let's see if there's anything else that I didn't cover that I want to. No, I think that's good. Okay. So don't worry, I'm not going to give you that on the test. Most likely what I'll give you is I'll say there's a race. There's this many people running the race. There are this many places. How many choices are there? That's obviously a permutation problem. Or I give you a case where you pick committees, which obviously, based on what I've told you, is a combination. The first test will be on Chapter 10. So we'll get through, what time is it here? Okay, so We'll get about halfway through section 4 today, and so I'm guessing not next week, but maybe the following Tuesday. Okay, so that's the Tuesday of the 4th week of the semester. That's my initial estimate. It would either be Tuesday or Thursday, depending on how things go. Yes. Yeah. So for people who haven't had me before, you do get to use a cheat sheet. So there's no memorization. You just have to be thorough in what you're writing down, and you understand what you're writing down. Don't just write stuff down. It's to help you so you don't have a failure memory, but don't use it as a replacement for understanding the material. Okay, so section 10.4 is called Using Pascal's Triangle. So Pascal's Triangle is a way of, it's for doing combination problems instead of having to use your calculator. So it gives you the answers for all those combinations, 7 things taken 4 at a time, whatever. And it also has some other uses. So I'm going to create it here, I guess. So here's Pascal's triangle. So you start with a 1 at the top, and then you write 2 1s on either side. So we're creating this triangle, so that's one corner of the triangle. And the outside of the triangle is always 1s. So this has 1 element, there's 2 elements here, there's actually 3 elements here. To get the resulting 1 that's between the ends, you add the 2 ones that are on either side. So what I'm trying to do is find, what do I put right here? And what you do is you take 1 plus 1, which are from the one above. So that's 2. So let me just move these down a little bit, okay, so that's the 3rd row, 1, 2, 1. Then you go to the 4th row, so you have 4 elements. You draw your 1s out here on the edges, and then you add those 2 to get this one, which would be 3. 1 plus 2 is 3, and 2 plus 1 is 3. So you get 1, 3, 3, 1. Okay, next one, we put another 1 out on the edge. So this is the 5th row. We add these 2 together, these 2 together, those 2 together. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. I'll do one more here right now. So put another 1. This is the 6th row. So we add these 2 together, those 2 together, those 2 together, those 2 together. So 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. So, at first you may say, well, that's kind of interesting, but is it of any use? And it turns out it is. Once you construct this, it's easy to construct. It's back to the last semester for you guys had me. It was like the Fibonacci sequence. That at first it said, oh, that's an interesting thing, but is it any use? And we saw that the ratio of the 2 adjacent elements approached this number, phi. So hopefully you could see how I could make this as big as I wanted to. So what is the use? What is the significance of those numbers? Well, there's two significances to them. So let me delete that page. So here's Pascal's triangle. It's in your book. Goes through the 10th row. So I went as far as this row, 1, 5, 10, 10, 5, 1. One thing you'll notice is that if you add the numbers together, 1 plus nothing is 1, 1 plus 1 is 2, 1 plus 2 plus 1 is 4, and you add those numbers to get to 16, 32, 64, 20, 128. So these are all powers of 2. 2 to the 0, 2 to the first power, 2 to the second power, 2 to the third power. So that's kind of cool. That's not the important part yet, though. what I've got over here, let me show this by itself. Wrong page here. There we go. And let me zoom in even further because it's hard to see out there. Zoom 150. Okay, there. So I can also create this triangle where the first number is the row number. So this is row 4. So these all have 4 for the first number. And then the second subscript is just 0, 1, 2, 3, 4. So you always start with 0. And these C's are not just coincidentally the same letter that's used for combinations. They are combinations. So it turns out that the numbers in the Pascal's triangle are the values for these combinations. 6 things taken 1 at a time, 6 things taken 2 at a time, etc. So you could use, if you had Pascal's triangle written down, you should be able to, without having to use your calculator, you should be able to find out what the combination values are for different values of n and r. So for example, if I wanted to know how many combinations or how many subsets can I have if I take 7 things 3 at a time, that's going to be the 7th row and the 4th number. So I go back to my previous page and I go to the 7th row, and the 4th number is 35. So that's the answer. I could do it, 7 factorial divided by 3 factorial divided by 7 minus 3 factorial. I could do all the math, or I can just look at it directly from Pascal's triangle. So that's the whole idea. That's the whole section, really, is that fact. So the other use of this thing is, let me just, So before I do that, like 5 things taken 2 at a time where order is not important, I would go over here, 5th row, and I would go 0, 1, 2. So that's 10. That's how I get that number. 9 things taken 4 at a time, the number of subsets, you go to the 9th row, 0, 1, 2, 3, 4 is 126. And 7 things taken 5 at a time, you go to row 7, and you'd go 0, 1, 2, 3, 4, 5. You get 21. So that's how it works. What you're responsible for is to be able to write Pascal's triangle, create Pascal's triangle. Okay. Now, let me add a page here. What's the other use of Pascal's triangle? All right, let me go back and go somewhere where we can actually see Pascal's triangle. Okay, add page. Okay, so here it is. So this is a little Algebra 2 review. A plus B to the first power is A plus B. Okay, so anything to the first power is just the number. If you take A plus B times A plus B, which is A plus B squared. If you use FOIL, you multiply FOIL, so it's A times A, so you get A squared. Then you have the inner FOI, I always do the wrong one, but outer would be A times B. Inner would be A times B. And last would be B squared. And then you can combine these two terms. You get A squared plus 2AB plus B squared. So if you look at the coefficients in front of these terms, the coefficient in front of A squared is 1. The coefficient in front of B squared is 1. So the coefficients are 1, 2, 1. Okay. So we go to a Pascal's triangle on the second row and we see 1, 2, 1. So, again, this is kind of using inductive reasoning. We tried one example. the numbers matched up. You're like, oh, maybe that's interesting. But you wouldn't stop there. You wouldn't say, well, the rule is this is going to work forever. So you could do a few of them. And I'm not going to work out, I'm not going to do the whole calculation, but if you did a plus b cubed, you would end up with a cubed plus 3a squared b plus 3a b squared plus b cubed. And again, the coefficients are 1, 3, 3, 1. There you go, 1, 3, 3, 1. So not only does Pascal's triangle give you the values for the combinations without having to use your calculator, it also gives you the coefficients in front of these expansions of a plus b to some power. So a plus b to the 7th power would be a to the 7th plus 7a to the 6th, b to the 1st, and you just start going through the sequences. So that was kind of cool, which I didn't know. I never learned that, so that was something new for me. Okay, what time do we have here? Okay, so the problems in section 4 are really just like problems in section 3, except you can use the Pascal's triangle to get the answers, or you can just use the procedures learned previously. So it's not any different, it's just a way of getting the numbers. So this, I don't know what number this is, but obviously I've taken it out of the book. It says a committee of 4 congressmen will be selected from a group of 7 Democrats and 3 Republicans. Find the number of ways of obtaining each result. So the first question is, how do you get it? So you've got a committee of 4 people, exactly 1 Democrat. That also means if you choose 1 Democrat, how many Republicans are going to be on the committee? 3, yeah, because there are 4 committee members. If one is exactly 1 is a Democrat. So the way you do this is it's a 2-part process. The first thing you do is you pick a Democrat, and then you pick a Republican, or pick the number of Republicans. So for this particular problem, and order is not important because it says committee. Okay, so we know to use combinations. So we have 7 Democrats. We're going to pick 1 of them. So that'll tell me how many different arrangements I can have for that first person on the committee. And then I multiply that by choosing the Republicans. So I have 3 Republicans and I have 3 remaining seats. And that product will give me the total number of different subsets of 4-member committees, given the fact you're only allowing 1 Democrat. Now, one of the rules, one of the things you'll notice from this Pascal's triangle is that anything taken 1 at a time is just the number. If I go back to Pascal's triangle, you'll see these are all taken 1 at a time. So 2 things taken 1 at a time is 2. 3 things taken 1 at a time is 3. So the first one is 7. There's 7 different choices. Because I have 7 Democrats and I have 1 seat. So there's 7 different ways I can do that. If you have 3 things taken 3 at a time, let's go back and see what that is, Pascal's triangle. 3 things taken 3 at a time is that one, which is 1, 2, 3. So it's the 3rd row. It's that one. So if this number is the same, it's always just 1. There's only 1 way because you've got 3 Republicans and 3 seats. So there's only 1 way you can do that. They all go and take that arrangement. So there's 7 total ways. Let's talk about two Republicans. So if I have 2 Republicans, that means I also have 2 Democrats. So exactly 2 Republicans implies exactly 2 Democrats, because I have 4 total. So now I do the same thing. Okay, I have 7 Democrats to choose from. I need 2. I multiply that by, I have 3 Republicans and I choose 2. So then I just have to use Pascal's triangle to get those numbers. And so let's do that. Let's find it. So let me erase what I did previously. So 7 things. So you go to row 7, 0, 1, 2. So there are 21. 21 is the first number. And the second one is 3. So I go to row 3 and I go 0, 1, 2. So go back to here. Row 3, 0, 1, 2. So the answer is 3. So I'm not calculating, I'm looking off Pascal's triangle, and so I'll get 63. Okay, now let me go make up a little more difficult problem. I'm going to do one, and then I'm going to ask you to do the next one. Okay, so let's say we have a committee of 3 Democrats and 4 Republicans. There are, let's say it's the Senate, so we're going to say there are 48 Democrats and 52 Republicans. How many different committees could I have? So it's the same thing as we just did previously. I've got 48 Republicans, 48 Democrats. I've got 3 spots for Democrats. So that's my first step, is to pick a Democrat to go on the committee. Then I have 52 Republicans. I need 4 Republicans. Because it's committees, I know to use combinations. I know to find the number of arrangements or the number of subsets for each step, and then I multiply the 2 numbers together. So to answer this question, all you have to do is you would take 48 Democrats, taken 3 at a time. I'm using combinations because it's committee. Then you have 52 Republicans, taken 4 at a time. Now, I can't use Pascal's triangle for this, so I'm going to, in this case, the first case here, n equals 48, r equals 3. Here, n equals 52, r equals 4. So now we just plug stuff in. So we'd have 48 factorial divided by 3 factorial divided by 48 minus 3 factorial. So that's the first one. And the second part is 52 factorial divided by 4 factorial times 52 minus 4 factorial. Now remember my little thing I just figured out this year, you know, to evaluate this, and we do it a lot, is all we have to do is take 48 and go down 3 numbers, 48, 47, 46, and then divide by 3 factorial. So the first one is just going to be 48 times 47 times 46 divided by 3 times 2 times 1. I've got 3 numbers in the numerator, 3 numbers in the denominator. Over here I have 52 times 51 times 50 times 49 divided by 4 times 3 times 2 times Again, 4 numbers in the numerator, 4 numbers in the denominator. I skipped over that step of canceling out 45 factorial. And now you plug the numbers in. So let's see what we get. 48 times 47 times 46 divided by 3 times divided by 2 divided by 1. So there are 17,296 committees or arrangements for the Democrats, and then there's 52 times 51 times 50 times 49 divided by 4 divided by 3 divided by 2 divided by 1. So there are 270,725, and you multiply those together, and there are a lot. 4,682,459,600 different committees that you could have. So now I'm going to ask you a similar question. All I'm going to do is, so it's the same problem, I'm just going to change the wording slightly. So we're going to have 37 Democrats, and we're going to put 3 on a committee, and we're going to have 63 Republicans, and we'll have an 8-member committee, so we'll put 5 on the committee. And the question is, what is the total number of committees possible? So first thing you're going to do is you say, oh, it's a committee, combination. So I'm going to let you put the numbers on here, and then I'll tell you what the answer is in just a second. It shouldn't take you very long to fill that in. So these are 8-person committees, 3 Democrats, 5 Republicans. Okay, so now go ahead and put it in, make it this form first. Don't do any simplification yet. Well, I'll let you just finish it up. So we'll give you 5 minutes to do that. That'll be the last thing we do here. And I'm just going to do it on my calculator. Ooh, that's a big number. So I was telling my other class this. There was on one of the news programs, there was this former CIA guy who ran for president. He was one of the minor candidates. And they were talking about the amount of evidence needed to publish an article in a paper. You know, you need somebody to say something. You need to have somebody back that story up. You need, a picture of the guy doing it or something. You need a lot of evidence to be able to publish something. Whereas if you are in the intelligence agency, you base your decisions. You're not having to go to a court or to withstand libel laws and things like that. You have to come to some conclusion that you feel confident, like bin Laden. Bin Laden's in this compound in Pakistan. We don't know for sure, but we've got this evidence. And if you wrote a newspaper article and said bin Laden's in this thing, but we haven't seen him, we don't have a picture of him, we don't have any DNA sample, something like that, you couldn't write an article about it. But they may have to you have to make a decision: do I risk American lives to go try to get this guy? Maybe it's a 75% chance. So they were looking at the evidence relative to Russia and Trump, and what they could publish versus what this guy, through his experience as a CIA agent, and what you would consider, would you go bomb somebody based on this? And on certain things that somebody does, basically what he was saying was that, you could probably count on this being a true statement, even though you couldn't publish it in a paper. So that was an interesting concept of, what's necessary to make decisions. And the example is, again, yesterday, Nikki Haley, who was the governor of South Carolina, she's going to be the new ambassador to the United Nations. She basically said, you can't trust Russia. We're not going to trust Russia. And you've got all these people in this administration that say, they're bad, Putin's a thug. And then you have the president saying, I love Putin. He's my best friend. And you think, why would he do that when everybody else is going the other direction? It just doesn't make sense. It just doesn't make sense, even though I can't write a newspaper article about it. And he could deny it, but when things line up. So if anybody, do you know what genealogy is? What's genealogy? Do you know? No? Anybody? No. Yeah, it's basically studying the relationship, your if you're looking to figure out who your ancestors are. And doing genealogy requires some same skills that the CIA would use in terms of, you can't be 100% sure sometimes that this person is your relative, but you can use things like, because you might have a married name, you don't know what their maiden name is, but if they were born in the county where the people who think your parent, this person's parents are, or some this time, which is within the time frame that somebody's going to have a child, and you make these suppositions, and you can come out, with experience, you can make a reasonably good guess whether they are in your family or not, even though you're not 100% sure unless you did the DNA test. Okay, so I got 5, 4, 6, 1, 4, 1, 4, 1, 1, 9, and let me see how many 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think there's a 0 on the end here. So it's a big number. If you multiply it, what I did is 37 times 36 times 35 times 30, 63, 62, 61, 60, blah, 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 and then divide by that. So I'll double check that, but that's, and I'm going to go ahead and assign section 4 homework. So this, we're almost finished anyway. It's not a whole lot of additional things. That'll be due next Tuesday. Or what is today? Thursday. Next Thursday. Yeah. So that's due next Thursday. Okay. We'll see you next week. Make sure I got everybody in here.